Okay, so this is the third problem from lecture today. We're in section 5.1 to 5.3 of the textbook. And we are looking at, basically, we just combined everything we've done so far this semester into P over AE. So we started with stress is P over A. Then we found that there was a relationship using Hooke's law between stress and strain. And strain was just change in length over length. So we can apply. Okay, we can put these equations together and come up with this deformation equation. So we have a hollow steel tube 1 with an outside diameter of 2.75 and a wall thickness of 0.25. It's fastened to a solid aluminum rod that has a 2-inch diameter and a solid 1.375-inch diameter rod. Okay, so we want to figure out the change in length of the steel tube. So if I want the change in length of the steel tube, that's from A to B. I have to recognize that's the internal force of A to B, length of A to B, area of A to B, and E of A to B. Okay? Then I want the deflection of joint D with respect to A. So we want the D with respect to A. So that's going to have to include this deformation, deformation, deformation. So I've got to sum up all of my deformations. So I'm going to have deformation A to B plus deformation B to C plus deformation C to D. And then we want to find the maximum normal stress. Well, normal stress is stress equals, okay, normal force over A, and that normal force, because we're looking at axial, is going to be F over A. So I need to find the normal stress from A to B, the normal stress from B to C, and the normal stress from C to D so that I can compare which one has the greater stress. Okay, so I'm going to start like I always do, and I'm going to rewrite all of my material information so that I have it and it's easy for me to find. So this is hollow, and it's steel. Okay, and it has a modulus of 30 times 10 to the third KSI, and it has an outer diameter of 2.75 inches, and then it gave me the thickness. Well, I know that area is pi over 4 outer diameter minus inner diameter, so I really need that inner diameter. So let's just draw a picture. When in doubt, draw a picture. So I have an outer diameter, okay, of 2.75, but it's hollow, so it actually looks something like this. Okay, and I need that inner diameter if I'm going to use this equation. So I can see that that inner diameter and the thickness is 2.75. So 2.75 is my outer diameter, and that's got to equal thickness plus inner plus thickness. So the inner diameter is 2.75 minus 2 times the thickness. So I get an inner diameter of 2.25 inches. Okay, so it's kind of messy in here, but here's my outer, here's my inner. And then we've got solid, and we are working with aluminum. And both of these last two segments are aluminum, so we have 10,000 KSI. And I have an outer radius of 2 inches. And I have an outer radius of 1.375. And here my area is just pi over 4d squared. Okay? So that's what I'm given for properties. And I have all of the applied loads. So if I'm going to find deltas or any of my internal forces, I have to set up a free body diagram with equilibrium to find the internal forces. So we have equilibrium and free body diagram. And I'm going to start, well, if I start over here on the right, I have to get these reactions, whether it's positive or negative, compression, tension, whatever. And that's a lot of work. So I'm just going to start at the left, like I do on every cake problem, and go to the right. I was looking for my post-it note. Okay, so if I'm starting on the left and I'm going to the right, I can see, okay, nothing has changed. This is the same. This is the same. Oh, I have a change, so I need to cut here. and I need to cut here. So let's start with this. Here's my segment, here's my applied load, and we're going to assume an internal that's tension. So I have 30 kips, and I have an internal force of CD, and then if I sum forces in the x direction, then I get negative force CD minus 30 equals 0. Do my algebra, so force CD equals negative 30 kips. And the negative tells me it's in compression. Okay, it's important because when I plug it back into my delta equation that I have up here, I will get a negative delta, which makes sense if it's in compression. Post-it note across, cut. So I can see here I have, here's my cut, I have 30 kips. Okay, I have these applied, 13 and 13. Because they aren't acting at the centroid, I would have to be concerned with some bending that occurs, but because they're symmetric and this would cause a negative moment, positive moment, we can just move these to the centroid without having to take into account anything else because there is no moment or shear stress that happens. We assume inside is in tension, and we set up our equation, and I have negative force BC plus 26 minus 30 equals 0. So I get that my internal force BC is negative 4 kips. That's kind of hard to read. Negative 4 kips. Okay. Now, I've got to start back here over the left, go across. We did that one. Now, here's our new picture. So, we have come across, I'm going to draw all of this. We have a change in material and diameter, and I have 30 kips. I have 26 kips. I have, okay, pressing here, 22 plus 22, 44, acting through the centroid. Plus, I'm going to assume in tension. Always assume in tension. Sum the forces in the x direction. I get negative FAB minus 44 plus 26 minus 30 equals 0. Okay, because I'm calling to the right positive. This is the only one acting to the right. And when I sum this up, I'm going to get that FAB equals negative 48 kips. So now I have all of these internal forces. And when I go back and look at, I'm going to slide back up again, force, length, area, E. Okay, for every material, I am given an original length. I am given cross-sectional property, so I can find that area. I'm given material, so I know E. The only thing I was trying to find is what are those internal forces, and I found internal forces as I go across. In fact, if I wanted to, I could come down kind of like this, okay, and I could actually draw an internal force diagram. That's my normal force in kips, just like we would do a shear moment diagram, and I would have a negative 48, and then I would have a negative 4, and I would have a negative 30. Okay, so there's my internal force diagram, and all of these are below, so I know they are negative and everything is in compression. Okay, so now I need to start answering questions. Find the change in length. Well, I was given. I just found FAB. Find the deflection at D with respect to A. I was given everything I needed. I found internal forces, and then the maximum normal stress. Well, that is internal force over cross-sectional area. So let's move this out of the way. And we can come up here if we wanted to put our information all at one spot. Let me find a pen that might work. And the internal force here, negative 30. Here we had an internal of negative 4, and here we had an internal of negative 48. Okay, so now I have everything written right up here at the top. So A. A. Delta from A to B is FLAE, everything from A to B. So I get negative 48 kips times 42 inches divided by pi over 4 outer minus inner, and I get a delta of negative 0.0342 inches, and that is from A to B. Okay, the negative tells me I'm getting shorter, which makes sense because I am in compression. Okay, so now if I want to know B, which is the entire delta, D with respect to A, then I need to find delta of each section. Well, I've already found it of the first, so negative 0.0342 inches, okay, plus negative 4, 30, A, E. Oh, I forgot to multiply this by 10 to the third, or 30 to the third. Sorry about that. I forgot to put my E. I got so excited about my area, I forgot to put the E. PLAE. Okay. Plus negative 30 times 24 divided by pi over 4, 1.375 squared, 10,000 times 10 to the third. Okay, so everything I have right now is in kips and inches. Kips and inches. And that's the biggest thing, is you need to be writing out kips and inches, kips and inches, kips and inches, KSI, to make sure that you have appropriate units. Both of these are negative because they're compression. They're going to end up giving me a negative, okay, delta, negative 0.0865 inches, which is telling me we are actually moving to the left. Okay, we are actually moving to the left. We are in compression, which makes sense. All of them are in compression. They all have negative deltas. We are actually moving to the left. So now for the maximum stress, well, the stress of A to B is going to be internal force AB, area AB. The stress of B to C is that internal force divided by area. And then we have CD is the force of CD, area of CD. So we have negative 48 kips divided by pi over 4 area outer, or diameter outer, minus diameter inner. Okay, stress BC, internal negative 4 divided by pi over 4, 2 squared, internal negative 30 kips divided by pi over 4, 1.375 squared. So I get a stress of AB of negative 24.45 KSI. I get a stress of BC of negative 1.27 KSI, and I get a stress of CD of negative 20.2 KSI. So what is the largest stress? Okay, that is the largest stress. So the largest stress I have is negative 24.45 KSI in segment A to B. How could I reduce this? What if that was beyond yielding? That was greater than the yield value that I'm allowed for that material. I could increase the cross-sectional area. If I increased the area, my stress would go down. Okay?